Okay, so I will talk about Coulomb gas in two dimensions. So, and the model is, of course, that of logarithmic interaction between particles. The potential interaction between any two particles is given by the logarithmic potential. So, and then, so we have n particles, and then we have well, how many pairs? N times n times n squared minus n interacting particles, and then we form this sum, which just tells us how much energy the interaction energy this configuration contains. All right. Now, but I said that we need also an external potential. So we put in an external potential. It's used to keep these particles that want to escape from each other. So to be able to keep them, contain them somewhere, we need something to help us to do that. And one way is to introduce a potential mathematically. So we put a potential V, which makes it energetically disadvantageous to be far away. Okay, so maybe I should try to draw here. You could think of it like this. I just draw it over one dimension. So you could this is the and then we could think about it like you throw in particles, and they are random particles, and dynamically, if you want to. You could think of it as Dyson gas, which is particles given a Brownian motion, each one of them, and then they interact with repelling force. So they will want to be here, and that's what I will talk about. All right. So let's look at the corresponding model. Is to now consider the total energy. Is the interaction energy plus the potential energy, of course. All right, the potential energy is given by the sum of potential energies of all the individual particles. So, particles, that's частицы, no? In Russian. Частицы. Okay, so we are thinking about, we need to understand the way to build to tell which configurations are more likely, and we want to just think about it like a situation where you have, we want to make sure that really that the low energy states are more likely than the high energy states, and there is a physical model which is called the Gibbs model, which approximates rather well the general quantum situation. And this Gibbs model it gives you that the probability density of a given state should be given by the exponential of minus a certain parameter, positive parameter, times the total energy. Okay. And then you normalize it by a certain constant. This constant, of course, is given by this integral. Okay, and then, we deal with the volume measure in Cn, the plane times itself n times, and then this is, of course, the same as the Euclidean space, 2n dimensional of the reals. And that's why I write 2n there. All right. To make this whole thing convergent, you should understand that you need the potential to be sufficiently strong near infinity, some kind of growth rate near infinity, so that you get convergence of this integral. Because remember, it was something involving interaction. And then plus plus the potential energy, and you really want potential energy to be such that this integral converges. And then what does it mean? It means usually if you work on it, it means that you need the polynomials to be integral with respect to the potential. All right. Now, so what we do is we introduce this probability point process. It tells you the probability of a certain position of particles, z1 through zn. You could think about this position of particles as it's just some, you draw them in the plane someplace, just as an instance. So below here we have the plane, and we think of the particles sitting in the plane. So we have n particles here. Of course, thinking about it as sitting in Cn is a bit impractical. So you just think about it like particles they are all located in one and the same plane. But with an ordering. So you order them. On the other hand, you don't want the process doesn't care about the ordering. Okay, to analyze this process, Pn, which gives the probability of a given configuration infinitesimally, then we would like to understand what's happening when you aggregate a lot of particles. So then it becomes impractical to talk about this probability Pn itself. So to get something that becomes more manageable, we deal with the so-called marginal probability measures, where we restrict to the first k variables. And the probability for that restriction is just you take that set, multiply by Cartesian multiplication by saying that all the other particles may be where they want to be. So you just take the total probability of wherever they are. You don't care about them, and then you get some probability measure just associated with the first k positions. Now it may sound strange to be interested in the first k. What about some other k particles which were not the first ones? However, if you look at the process itself, it doesn't care about the ordering of the particles. So this could be any pair of any k-tuple of particles. The numbering is not essential. Okay, and then what we do is we take the associated measures and we form something called the intensity measure. So this is renormalized. Remember, this is a probability measure. So this intensity measure is not the probability measure. It generally has a total mass which is bigger than 1. It's this number which is the total mass. And you can see it's related to combinatorial considerations. No, I did some push, yes. Okay, so I come to a first result here. And this theorem has to do with what happens when we add one more particles to the system. So go from n to n plus 1 particles, but you just study what's going on with the intensity of your k first particles. Which essentially is talking about the probability of finding in any little neighborhood, the probability of finding k particles there. So if k is if k is 1, you could say what's the probability of finding one particle in a very small place, and that's what would happen when you add change the total number of particles from n to n plus 1. You would think adding more particles should make the probability of finding a particle in any given little spot in the plane bigger, right? It should be true. Huh?
It does not depend on n, on v, on potential.
Does not depend on v, no. But it does depend on this number beta. Remember this number beta, which is we're talking about all possible potentials v here. So the assertion of theorem 1 is that for all potentials that are reasonable in terms of this integrability condition which is needed, then you have this monotonicity, that the probability, let's say, of finding one particle, the probability density of particles is monotonically increasing everywhere in the plane if you add one more particle to the system. Okay, now this statement is actually false in general for all potentials v if beta is bigger than 2. The parameter beta is called the inverse temperature of the system, and so if it's bigger than 2, then what it means is that your temperature goes down, that is, you get a bit more crystallization, and some unevenness appears apparently. So the meaning is that, of course, in total the intensity goes up, but locally it doesn't have to go monotonically when you increase beta. On the other hand, of course, it's extremely likely that for beta less than 2, where you increase temperature, then your system should be more evenly spread out, and then you would expect to get such a theorem to hold, but we don't know that. Okay, now I want to tell you something more about the structure, which is special about beta equals to 2. So here, in this case, we have a so-called determinantal process. So to explain what that means, we need the space of polynomials of degree less than or equal to n minus 1. And then we give this space of polynomials the inner product structure of this space L2 on the whole plane with respect to the weight, which is e to the minus v. Then, of course, under the standard assumptions on v that it grows sufficiently near infinity, then the point evaluations are bounded. Well, first of all, the polynomial should, of course, have finite moments with respect to, they should belong to this L2 space. But that's part of the assumptions you need. And then, well, okay, so what you obtain is, under reasonable assumptions on V, you obtain elements k sub w in the space, such that you obtain the point evaluation by this inner product representation. Okay? So if you want to think about it from the point of view of functional analysis, you take a polynomial, then choose a point in the plane. You take the mapping from the space of polynomials to this point in the plane. This is a linear functional on your finite dimensional Hilbert space. Of course, there must exist an element in the space which represents this linear functional by the so-called Riesz-Fischer theorem. And then this function, which depends on z and on w, is a function of z which belongs to the space. And then it turns out that, well, of course, it depends on w also, but the dependence on w is quite nice. So it's kind of the same as dependence on w. You just have a complex conjugates here. So it's so-called sesquilinear property. It has kzw is equal to kw z with a bar, for instance, like that. And here I tell you that it's given by it can be represented in terms of an orthonormal basis, but actually the sum doesn't depend on the choice of the orthonormal basis at all. and this kernel K is called the reproducer kernel. If you're interested, I could tell you that it depends, of course, on the potential V, and it also depends on the dimension n. N is the dimension of the space of polynomials. All right, now I told you about the intensities, but they're actually, why they're natural is, one reason is that you get this beautiful formula for the corresponding intensity. Now, to get Z there means Z is here Z1 through ZK. I should have written that. And then on the left-hand side you have a measure, on the right-hand side you have just some function. So what's wrong is that you should also multiply by the volume element with respect to Z, of course, in the corresponding space of 2K dimensional R real Hilbert space. Okay. Well, this it looks a bit strange when you have a large K, but at least if you choose a very small K, you could understand what's going on. For K equals 1, for instance, let's see what happens then. Then taking the determinant of a 1 by 1 matrix is very easy. Just take the value on the diagonal in this case, and you multiply by this exponential expression, and you obtain just this. The kernel on the diagonal times the exponential of minus the potential. And then this particular expression has a name, it's called the one-point function. Why do you divide by n in this case? Well, one reason is is that you might be interested in getting the probability density, because if you integrate here K Z comma Z times this expression, the weight in the plane, then you get by the formula defining the kernel, you will get the integral, which is 1 from each of the elements of the orthonormal basis. You integrate out and you get 1 plus 1 plus 1 plus 1 n times, and so the integral without dividing by n would be n, and then you divide by n to get probability density. It's the same kind of thing that made us choose the corresponding intensities in the way we did. We multiplied by a combinatorial factor. So this is like going back, leaving that, getting rid of that combinatorial factor again. And then with this special case beta equals to 2 it models the random normal matrix matrices. If you have any questions, I'm happy to answer. Okay. Next, we want to study where the particles are localized, where the particles are in the plane, given that n is very big. To get something, to be able to say something reasonable about this, it's not a natural thing to make the potential stronger, to just strengthen the potential by a factor as you let the number of particles go to infinity. And somehow the correct scaling here is to let the potential V equal a fixed potential Q times a scaling parameter called M. And M here should be thought of as a number which is essentially proportional to n as n tends to infinity. So we have two parameters. N is the number of particles, and we have the scaling parameter for the potential. And then what happens is that you're able to constrain the particles to stay essentially within a certain compact set. All right. So also in the determinantal case, what we really need to do is to analyze these polynomial reproducing kernels for with respect to the corresponding weight. Let's see. We continue. And I want to tell you something about the some heuristic thinking here. So we return to the total energy. We remember it's an interaction energy plus a potential energy. Now the potential is m times q, and then we get this expression. This is the interaction energy, and that's the potential energy. And then we see more clearly why we wanted to rescale the potential. So we take that, divide by n squared now. So we divide here by n squared, and here we divide by n squared. Next, we suppose that n and m, they're supposed to be more or less proportional to each other. So let's call the ratio tau. Okay? Then what happens is this. We get 1 over n squared as before, and then we have here m over n, that's 1 over tau. So we replace that by 1 over tau here. And what do we see? We see that we have something that looks like Riemann sums, right? You have almost n squared points, and then you divide by the number of them. So it's like a small contribution from each point, which should be approximately an integral. Here again, it's like you have n points, and you essentially you produce an integral. To be more precise about what's happening here, let's we define for a probability measure the corresponding energy, which is the logarithmic interaction energy for that measure, and then the potential energy. And then what we observe is that essentially the energy we consider divided by n squared is somehow more or less this, right? That's more or less, morally, it's this energy for q divided by tau, where sigma is the so-called empirical measure. It's you take your n particles and put mass 1 over n at each one of them, and add that up. You get a measure, a random, you could think about like a random measure, a random probability measure with respect to the ensemble. But then there is a problem here. Why don't I write equality? Well, there is a reason that here, if you really do take this measure, then you get, actually in this double integral, you get the possibility of having 2 points being the same. So you can choose one of them to be at, you will get the infinite contributions from the diagonal part of the integral. That's why this is not really correct. Actually, this will not be well defined. It will be infinity. But then to remedy that, let's just disregard the diagonal terms when both points are the same point. All right? So forget about it. Sort of formally, just you could think about like in this integral, let's remove the diagonal from the integration. Then we do get the right thing, and we write this with sharp there to indicate that we did this correction. We removed the diagonal terms, the singular part. And then we are in this situation. We had our model, the Gibbs model, e to the minus beta over 2 times this energy. And then we remember that the energy E was equal to this I sharp energy times n squared. Okay, what does it mean? It means that here we the model is trying to strongly force this energy to be very small, as small as possible. And we should expect the convergence to the lowest energy state. And to see what is the lowest energy state, we could, since we have this sigma is equal to the, well, d sigma was equal to 1 over n, d delta zj. You have a point mass at every point with each point 1 over n. Then in the limit, as you let the number of particles go to infinity, this could go to some kind of smooth measure. Some kind of special smooth measure. And to see which measure it should be, we try to minimize this energy. Let's see if I can go back. Maybe I should go back. So we are now trying to see what is the minimum of this energy over all possible compactly supported probability measures in the plane. All right. By the way, I should say that here, if you look at such a problem, suppose that you remove this term, and instead of integrating over the whole plane, integrate over a compact set in each variable, the same compact set. Then you know what the minimizing measure is then. So if you would do just this, integrate over k, and then we have log interaction energy. It's the standard equilibrium measure, which is also has another name. It has a name of harmonic measure. It's harmonic. So what happens is you have your k here, and you have your point at infinity, and at the point at infinity you throw out a Brownian particle, and it's a hitting probability at the boundary of this of that.
So you mean that you
compact set.
disregard the second integral, right?
If you throw it away, yes, you throw it away, and you restrict to your compact set. What it actually it is a special case of this model actually. If you put q to be plus infinity outside the compact set and 0 on the compact set, you do get exactly this problem. Okay, so we have the analog of Johansson's marginal measure theorem, Kurt Johansson. The theorem says that under the reasonable assumptions you can put on the potential q, you get this convergence, that the marginal probability measure for a k-tuple converges in probability to the corresponding measure where you have equilibrium measure corresponding to this parameter tau in each variable, and the process completely forgets in the limit as n tends to infinity. It forgets the interaction between these first k particles. It just disappears, and each one tends to the equilibrium measure. Probably, but I'm not a mathematical physicist, so but probably this is could be viewed as a case of fermionic convergence to bosonic behavior, I would imagine. Bosons, they don't care about each other. They are not repelled by each other. While fermions, they can't be in the same state, but in some big limit, they tend to lose this repulsion effect. Okay, we come to one more part of the general understanding of the problem, So we now look at this so-called obstacle problem, where you take the supremum over all, pointwise, over all functions q, little q, where q, the little q is less than or equal to this capital Q, and then little q is taken from a specific class of functions. The class of functions is the functions called the subharmonic with parameter tau in the plane, and they have this kind of behavior near infinity. Okay, where would you get such a class of functions? Take a polynomial of degree less than or equal to, let's say, well, n minus 1, for instance. Then you take log, just log of p squared. And then finally you divide by, what is it? M, maybe. I guess like that. Then you would have a function u, which is of this type, right? So this is kind of a potential theoretic model corresponding to polynomials. You take logarithms of polynomials, they don't grow too much near infinity, and you somehow want to keep this in your potential theory model. So then that becomes a natural condition. It's like trying to keep something from the information from the polynomials. And then, all right, we need also the corresponding logarithmic potential associated with a measure. So q hat here is the solution to this obstacle problem. It's you maximize over all little q functions. So it's an obstacle problem. So it means that it's associated with a free boundary and so on. This is the typical situation, free boundary. And so you get two phases where you get lift from the where little q, the maximal little q attaches to is able to reach up to the given potential q, and there will be a free region where it lets go. So what will happen here in this model is, if I draw here instead q, then what will happen here is that there will be some region where q hat is equal to q. There will be some region here where that region is the region where the particles live. Okay, now here Frostman's theorem says that it gives the relationship between the equilibrium measure and the solution to the obstacle problem. So the solution to the obstacle problem is just equal to a constant minus tau times this logarithmic potential associated with the equilibrium measure. So these problems are the same. That's interesting to notice. And then let's look at the support set here. So the support set is then going to be essentially this set where you have touching of where this q hat, the solution to the obstacle problem, and the obstacle, the potential, where they touch each other, where they're the same. Coincidence set is called. Then you have this theorem from this theory of Kindler, Slopakia, etc. So under some smoothness on the potential, we do have this relationship that the Laplacian of the solution to the obstacle problem, it is equal to, has the same density as Q, only restricted to a certain set. And what it means is that the equilibrium measure is indeed a nice measure with smooth density, except that it's it's a cutoff of a smooth density. So a remark here then is that to understand the dynamics of the equilibrium measures in this two-dimensional situation, it just reduces to the study of the support sets. Because the density is understood, so it just remains to understand the supports. That's not true in the one-dimensional theory, but because that's a singular kind of theory. Here is some words about the comparison with the emission ensembles, and it's possible to get the emission ensembles as a limit of the ensembles considered here. Maybe I shouldn't say that much about that. Let's go on to so-called linear statistics. What are linear statistics? Well, it's just you take a function, a bounded continuous function, and you just form the sum of the values at these points z1 through zn. Now remember that z1 through zn, those are points which are selected given by this probability distribution which I told you about. So we're interested in understanding the behavior of this so-called, we call it the trace, or samples. So we sample, take the average of all the values at these points and wonder what's happening with that as n tends to infinity, and then it's an easy exercise to use this theorem of Johansson to which was generalized to this setting to obtain this statement that the average tends to, for each given test function f, it tends to this integral against the equilibrium measure. Okay, now for fluctuations, we try to analyze more deeply the trace. So then, first thing is to understand where is this expectation, how to analyze it carefully. Can we tell what is the expected value at least? Well, from before we knew from the theorem that on the previous slide, that you get, if you divide by n, you get this inner product, or maybe not inner product, but just I write f comma sigma hat for the integral of f d sigma hat. Okay? Then we would get, so if you divide by 0, by n, this tends to 0. So let's see, what would be the proper rescaling? So we subtract off n times this and try to understand how that behaves. So, usually you would probably multiply by square root of n instead of multiply by n, but because of some repulsive effects here, it's natural to multiply by n. And then it actually converges to something. So the expected value of this sum is this number for smooth test functions f. Here things are a bit complicated. 1 sub s is of course the characteristic function of the set s. S, we assume tau is 1 and we don't write tau anymore. And L sup s is something else. Capital L is the logarithm of the Laplacian of Q, and L sup s is, what is it? It's you restrict L to the droplet S, the support of the equilibrium measure, and then you extend this function harmonically outside the droplet. This is what happens. And then, to make things complicated, we of course have to take the Laplacian of the whole thing, which means that this is some terrible distribution, but since f is smooth enough as a test function, we can still calculate the whole number. So for a given test function, what happens here is that this is some number. And so it describes what happens here with the expected value of the trace minus the object which we calculate, the integral of f against the equilibrium measure. Okay, now on to the fluctuation theorem. So if you take the trace and you remove the expected value, what happens is that this tends to a normal distribution. And the normal distribution has this variance. So remember what we did. What we have to do. We take f. This is our smooth test function. Then we do this f sup s thing. What did we do? We took f, restricted it to the droplet. And then outside, we replace it with the harmonic function with the same boundary values in the exterior domain. And then finally, after we have done this, we take the gradient and take modulo squared and integrate. We do the Dirichlet form, the corresponding Dirichlet integral in the whole plane. Now, here comes some discussion of what is the technical background here. So let me skip this page. Let's see. Yes. There is also this. Yeah. Okay. Here I can say something about what is known about kernels. So it's if you take kernel, the standard Bergman space, and you do take such a weight, it's possible to have an expansion theory for the Bergman space. But here we actually are interested in the polynomial kernel, so it's not the whole space. And so the natural question is, what happens then? And still, it is possible to model inside the droplet. You can get a good expansion theory for the reproducing kernel function. And then, of course, it's also possible to this kind of statement also has a polarized version, so that when you have 2 points z and w which are close to each other, so the pair is close to the diagonal, you have a polarized version of that statement. Okay. And one way we analyze the behavior for large n is to analyze the so-called Bayesian measure. Why is it interesting? Well, you take k as a function of z and w there. You fix w. And then think about this whole thing as something that depends on z. Then it's easy to see that this object is a probability measure. And so for a given point w, you could be interested in what way does this actually behave for a fixed w. How does this behave as you let your parameters m and n tend to infinity in the corresponding fashion? That would be a way to model the behavior of the kernel. And it's interesting actually to see that it's possible to understand this, at least in some specific instances at first. So in fact, more generally, if the point w is outside the set S, here's the set S, where we have the coincidence set, and then if you choose a point w outside, then this Bayesian measure, it does converge in a nice way to which measure? Well, it turns out this measure which has to live on the set S, on this compact set S. So which measure should it be, if you would guess? You have some measure on the set S, which is supposed to be associated with this point W. What's the most natural way to define? What is the most natural way to get such a measure? Yes, of course. So you again from W you start the Brownian motion and consider the hitting probability on the set S, and this is the limit. In fact, this is not a trivial statement, but it is true. On the other hand, if your point W is inside, this measure converges not to a harmonic measure anymore, because that's kind of trivial. It's not. There's no reasonable harmonic measure starting at this point, with a hitting probability for hitting the set where you are already located. What you would think should be true here is it should be converged to the delta. I mean the point measure at W, and that is true. But then it's even more interestingly possible to analyze how it converges to a direct delta measure. So if you blow up to the right scale, suitable scaling, then this for points inside, if you blow up for point inside, you can get very accurate a very accurate analysis of this Bayesian measure, and it tends to the Dirac delta measure approximately along a Gaussian family. A symmetric, rotational symmetric Gaussian family. And then what it means for the process itself is that if you blow up at the interior points of the ensemble, then you get convergence to one and the same process no matter where you are located. The blow up to the suitable scale, it has a limit, and so the process will be essentially the same at every bulk point. Let's see. Yes. Okay, I should say something about boundary behavior, because that's really quite interesting. So what would happen if you were on the boundary, or if you would try to blow up the Bayesian measure when you're near the boundary? Then things are more complicated, but it's still possible to analyze what happens, especially in the Genebra ensemble case. Genebra, it is the case when z modulus q is equal to z modulus squared. So it's rotationally invariant and this kind of harmonic oscillator potential. Okay. Well, if you blow up the kernel, then at this boundary point, things become rather interesting, and in fact, the limit of the kernel of the reproducing kernel function is can be understood in terms of the classical error function. This should be a universal thing, but for smooth boundary points. But there is no such theorem yet. And here, well, okay, we expect to have a lot of universality here. So, well, usually what happens is that we observe that we get, if you make a blow up, you usually get some specific class of Hilbert spaces of entire functions. And these Hilbert space will depend on the typical situation. So in here, it is at interior bulk points, you get the classical Brugmann-Fock space of entire functions with with the Gaussian measure. And then if you look at the Gaussian unitary ensemble, which is a specific case of the when you have eigenvalues in the real line with a Gaussian potential, then we have typically the sign kernel at the bulk points, and that's associated with another space of entire functions, the Paley-Wiener space. Now, at the boundary, we also have the Airy process in that case, but then the scaling is a little different. Why it's a different scaling has to do with the fact that in that case you have a lower density of points near the boundary. So some words about what to do with the boundary points, because the interior points we understand quite well what's going on there. So what you really need is some reasonable asymptotic expression for the corresponding orthogonal polynomials. This is possible and well known to do. That is possible to do in, let's say, the Hermitian case, but here in this complex case, it's difficult. There's some kind of thing that is stopping us from really analyzing the behavior. And then if you know that, you should also be able to analyze the so-called free energy and obtain a rather complete expansion of the free energy for inverse temperature beta equals to 2. Okay, just a word about something about polynomials in Z and Z bar. We discussed here only polynomials in Z. Now, but it is necessary, however, possible to consider polynomials which depend both on Z and Z bar, where, for instance, the dependence on the complex conjugate of Z is very low. So the degree is at most q minus 1, and the degree in Z is at most n minus 1, where q is very small and n is grows to infinity. Now, in this case, here we analyzed with my student the Genebre case, and then we also analyzed the expansion of the kernels, reproducing kernels in the rather more general case later. Let's see. So I come to the bibliography, so I'm approaching the end of the talk here. I should probably have said that also that more recently Silvia Serafati has been working on related topics and obtained results on for instance, on higher dimensional Coulomb gases. But here is these results that we were obtained with my co-authors Amer and Makarov. Here is we have 3 papers, and then there's a related paper by Berman. There's a paper by my student Jaime. There's a joint paper with my student Jaime, and well, the second paper with Jaime, and then this is a paper where we talk about these Coulomb gases and in relationship with Laplacian growth. The Laplacian growth is really the process of adding more particles, letting the parameter tau grow. What happens then? Then this is understood as Laplacian growth. And then there's a somewhat related paper with Nieminen. And again, because of the Laplacian growth is essentially the backward Hellish-Hopf flow, and some results apply especially from this paper with me and Shemorin. And here is Johansson's rather well-known paper on the fluctuations in the Hermitian case. Okay, so I guess I'm more or less finished.
Есть ли какие-нибудь вопросы?
Вопросы?
Можно тоже.
Сложно, да? Все понятно.
Не просто.
Does this method only work for Coulomb? I mean, when you have inverse logarithmic interaction?
Which the determinantal structure is specific to 2 dimensions, and also specific. Well, it happens also in 1 dimension if you do it like Kurt Johansson and others did. but it's specific somehow, and you don't get determinantal structure in higher dimensions.
I mean, if you choose not logarithmic, inverse logarithmic interactions, but a different one.
If you choose other interaction, yes. So if you would look at like 1 over z to some power alpha, right?
For example.
You don't get determinantal structure. So it's different.
This way, what happens?
I think that is still you get something related to obstacle problems as the kind of large-scale structure, but I'm not clear that you can get such strong asymptotic behavior, because it could be that things are a little different here.
Anything else? Okay, if not, let's thank the speaker again.
I have something more I want to say. Can I get this other file? I would like to give you a picture.
So it's on the desktop.
Maybe I should have started with this picture, but now that I talked about this whole thing, let's try to end with a yes.
Maybe.
Yes, that's okay. It's okay. So here, I would like to ask you. This is not it's a computer image which I got from somebody else, and I would like to ask you to look at only one of the colors. There is blue and there is red, but let's say you look only at one of them, and then, for instance, blue. Then this models. This is this so-called Genebra model. So you look at beta equals to, sorry. Okay, thank you. So you look at beta equals to, this is a model, this is a run of, typical run of beta equals to 2, and where you have potential Q equal mod z squared. So this is what you typically get. You get a big blob. Here in this case it gives you a circular disk, and you get a certain density of the points. But you also see a finer structure. You look more carefully, you see that they tell a little bit repulsion between the points. They don't want to aggregate too closely somehow. On the other hand, it's not so rigid. So you look at it and you see that it's not really that crystal-like. There is some liquidity here. But what you would expect, if you reduce this number beta, you make it beta grow. I mean, if you let beta grow, then you will get more and more crystallization. It should look more and more like a lattice. That's the expectation. Could you guess which lattice you should get? Sorry? Yes, of course, something like that. Yes, it's usually thought of as a equilateral triangular lattice, but of course it can also be explained as the honeycomb lattice. Yes. Exactly.
Why it is, of course, honeycomb?
Of course. Well, you feel it's some kind of packing problem. It's some kind of packing problem, and how densely can you pack points in the plane somehow? But because you have a large-scale interaction, it's a little bit trickier than that. But some kind of packing problem. Okay, so that's all I wanted to tell you. This is supposed to be a run where the blue and the red are independent. So you see, there's no real repulsion between red and blue, but yeah. Okay.